today's class, we're going to talk about the history of the discovery of the atom's interior architecture, and we use as a starting point the cathode ray tube. Scientists found that when you evacuated a glass tube and you put two electrodes on either end of the tube and applied about 15,000 volts, that what you got was a stream, a green line would appear going from the cathode to the anode. So it was attracted to the anode because it was a negatively charged particle of some kind. They also found later on that if they put an electrical charge close to it, they could cause it to deviate depending on which way, which polarity the charge was. So a positive charge would cause the stream of electrons actually to curve towards it. A negative charge would cause the electrons to stream upwards, and same with the magnetic field. So they were also able to find out that the electron had a negative charge. They were able to find its charge to mass ratio. They eventually discovered that the electron was 1,827th of the weight of a hydrogen atom. It also led them to understand that the nucleus of an atom had to have a positive charge to offset the negative charge of the electrons. What they didn't know was the architecture, the interior structure of this nucleus, or the position of all these different charges. And many theories were forwarded. Proton was discovered in 1886. Around that same time, Moseley did an experiment that exploited the use of cathode rays to find out the number of protons that were contained by the nucleus. He found that when you bombarded different metal targets with the cathode rays, with this ray of electrons, that it generated X-rays. And he found that the frequency of the X-rays varied according to how many protons were in the nucleus. So with that, he was able to reorder the numbering of some of the elements in the periodic table. Some of them had been flipped in the original periodic table. Because of Moseley's experiment, they were able to correct those errors. And then Ernest Rutherford came along around 1904. He proved that most of the mass in an atom is concentrated in the nucleus with his famous experiment using a radioactive piece of metal. He put it inside of a lead block and had a very tiny hole in the lead block that allowed the radiation to come out in a straight line. And he put a gold leaf target in front of the radiation. What he expected was for all the radiation to be stopped by the gold leaf. Instead, what he found was that most of it went through. 98% of the radiation went through, but on the occasion, he would get a nucleus being reflected. He would get a reflection of the radioactive particle. It would bounce off and come almost straight back. And his characterization of that was to say it was like firing a howitzer at a piece of tissue paper and having it bounce off. What he finally concluded from his experiment was that most of the mass of the nucleus was concentrated in the nucleus. Most of the mass of the atom was concentrated in a very small nucleus that had a very small profile. To give you an analogy, it would be like putting a marble in the middle of a football field. So the electrons would be whizzing around in the space of the football field, and the nucleus would be a tiny little marble in the middle of that field. So what are the chances of hitting the marble if you threw another marble? And that was what Rutherford's experiment was like. And if you could imagine an atom scaled up to that size, say it would weigh about 100 tons, well, 99 tons would be concentrated in the nucleus. Now, I'm not quoting the numbers exactly, but it gives you an idea of what the atom is like. The atom is mostly empty space. However, you wouldn't be able to walk into the football field. As soon as you touch the edge of the football field, you would feel like a force field pushing you back, and that would be caused by the electrons moving around really quickly within the whole volume of the football field. Chadwick later discovered or proved the existence of neutrons. So neutrons have no charge, but they have the same mass as a proton. And so at around the 1920s, the atomic architecture included protons, neutrons in the nucleus with electrons in orbits. And they were found to fit in certain orbitals, which we were going to discuss a little bit later over here. I just want to show what a typical helium atom was believed to look like around the 1920s. So they would have 2 protons and 2 neutrons. So that's why helium has an atomic mass of 4, and the 2 is the atomic number, symbolizes the number of protons. So whenever you draw the symbol of helium, for example, you'll put a 4 over here and a 2 over there. That's the mass number, and it represents protons plus neutrons. This number represents only protons. So if you want to find out how many neutrons are in a nucleus, subtract this number from that number. So for example, sodium has a mass number of 23, it has an atomic number of 11. It means it has 11 protons, and protons plus neutrons equals 23. So if you subtract 11 from 23, you get 12. That tells you the number of neutrons. So protons plus neutrons minus protons gives you neutrons. So here's protons plus neutrons, here's protons. And neutrons are defined by subtraction. This was the model of the atom that they suggested. It's sort of like a planetary model where you have a sun at the center and the electrons are behaving like planets. But there's one very fundamental flaw with that idea. And the idea is that if you have electrons circling in fixed orbits, you have a charged particle accelerating continuously. And scientists, even in the 1920s, knew that when you accelerated charged particles, you create a magnetic field. Or you create an electromagnetic field. The idea of the antenna is based on that. In an antenna, you have an aerial, a piece of metal, standing up in a line, and you have electrons moving back and forth in the antenna. When the electrons move back and forth, they generate electromagnetic waves. And those electromagnetic waves will then transmit through space. They can be captured by another antenna. If you have an antenna sitting here, an electromagnetic wave comes close to it, it'll start moving the electrons the same way. The same way a water wave will move a cork floating up and down. So the electrons in the antenna can be likened to a cork, and the waves, the electromagnetic waves passing by the antenna make the cork move up and down. Those electrons moving up and down generate a current, which is then detected by the circuitry of a telephone or whatever you're using the signal for. So the scientists knew that by having electrons going in a circle like that, it should have been setting off electromagnetic waves, and eventually the energy, unless you're pumping energy into it continuously, that electron would spiral into the nucleus and disappear. But that's not what was happening. So there had to be a better explanation. Their model of the atom was incomplete. So this is what they teach you in grade 10, more or less, the Bohr-Rutherford model of the atom. But then they had to refine the technique, they had to refine the hypothesis to include this idea that you can't have an electron going in a perfect circle around the atom without generating an electromagnetic wave. So on the second board now, I've summarized this idea. Newtonian physics suggests that electrons should spiral into the atom and release energy as it does so. If this were the case, all matter would collapse or explode. And that doesn't happen, so there had to be a better explanation. This observation led Niels Bohr to postulate the quantization of energy levels in the atom. Using hydrogen as the model, why did they use hydrogen? Well, hydrogen is the simplest atom. It's got one proton and one electron. So any calculations that involve momentum, electrostatic attraction, and electromagnetic energy are going to be made easier if you have fewer variables. And here you have only one proton, one electron. It makes the calculations easier. So that's what Niels Bohr focused on. And using hydrogen as the model, Bohr calculated that the energy of the electron can be described by E is equal to R over n squared, where, misspelled, E is the energy level, R is the Rydberg constant at 2.18 times 10 to the minus 18 joules, and n is an integer value. And he found that he could explain the spectrum of hydrogen based on this formula. He said there's these lines that appear when you make hydrogen get really hot, and then take the light that it generates and put it through a prism so it spreads that out into a spectrum. You see these four lines. The distance between those between the four lines can be explained by this formula. So this formula explained the excitation spectrum of hydrogen, which produced four lines: violet, indigo, blue-green, and red. So Bohr came up with a theory to explain what was happening in the atom. And the first hypothesis of his postulate was that every hydrogen atom has certain paths in which the electrons are allowed to move. The second idea was that each energy level corresponds to a spherical shell. Later it was determined that the electrons don't actually only move in spherical shells. S-block electrons move in spherical shells, but it turns out that P-block, they move in lemnis case. They look like figure eights. And in F-block, they also look somewhat like figure eights, but they're oriented in different angles. The third hypothesis was that electrons travel in orbitals without loss of energy. So he making a jump in thinking here. He was realizing that the electrons have certain paths which they stay within when they're close to the atom, and they will jump to another path further away from the nucleus, but only with an input of energy. And when they fall back down into their old orbital, they release the same amount of energy as it took to pump them up in the first place. You have to remember, the electrons, they calculated, move at something like 2/3 the speed of light. So within that tiny confined space of the atom, the electrons are covering about 120,000 miles per second. If they think of one atom, one tiny little atom, and the electrons in there are whizzing around at 120,000 miles per second, roughly going around the Earth 5 times a second, but within that space of the atom. The fourth idea, he said, was that the only way an electron can change its energy value is to jump from one level to another. And during the jump, either a photon is absorbed or emitted. So if the electron is jumping up, you've got to put energy into it to make it go to the higher level. If, on the other hand, the electron falls from a higher level to a lower level, it emits a photon. And the idea of the photon is basically the smallest value of light energy that you can measure. And there was an idea that Max Planck came up with. He said that essentially light is pixelated. If you look closely enough, if you do the calculations in small enough numbers, you start to notice that light comes in discrete packets called photons or quanta. Light is not continuous. Scientists always believed before that point that light was continuous. Actually, there was a scientist by the name of, I don't know, the name escapes me. Newton and the scientist had a disagreement about the nature of light. One of them said it was corpuscular, meaning it was like photons, and the other one said that light was a wave and it was continuous. Turns out both of those properties are true to a certain extent. So they found that the energy emitted by an electron jumping from one energy level to the next is predicted by E is equal to h nu, where h is Planck's constant, 6.626 times 10 to the minus 34 joules times second. Mu, which looks like a V, is the frequency of the light emitted in hertz. And if you're not familiar with hertz, hertz just means cycles per second. So for example, a guitar string, the second thickest guitar string vibrates 440 times a second if your guitar is properly tuned. So it has a frequency of 440 hertz. They just say hertz as a way of saying cycles per second. It has units of seconds to the -1. They don't write the cycles part. They just write the seconds part. And finally, the energy is measured in joules. So the energy of a photon is measured in joules using this equation.